Okay, hello, welcome to today's lecture. So what we learned so far? We start talking about a random variable. Suppose x is a random variable. This random variable can be discrete or it can be continuous. For a discrete random variable, we talked about discrete probability distribution. Discrete probability distribution, and we use histogram to actually visualize the discrete probability distribution. So here you have your x, here you have your p of x. If x is 0, then your first bar, for example, your first bar is just right here. When x is 1, this is your second bar. X is 2, this is your third bar. And 3, suppose this is your next bar. We use a histogram to visualize discrete probability distribution. Very well. We also learned about different probability distributions for a discrete variable. We have many probability experiments, and one of the important ones is a binomial experiment, binomial probability experiment. Binomial probability experiment. Remember that for a binomial probability experiment, we had 4 important conditions, with 4 conditions to be checked. Then we say that, hey, the binomial probability formula, binomial probability formula is defined this way. P of x is equal to n factorial divided by n minus x factorial, p to the x, q to n minus x. Okay, after defining the probability formula for a binomial experiment, we say that, hey, we can graph this probability binomial distribution by using histogram. Very well, in this case, using the discrete probability distribution or discrete probability histogram. So let's see. Okay, so in chapter 4, our main focus was on discrete random variable, discrete probability distribution, and its histogram. In chapter 5, we introduced a continuous random variable. So for a continuous random variable, we have the probability distribution, which is called the continuous probability distribution. So continuous probability distribution. Very well. So one of the most important continuous probability distribution is actually a normal distribution. One of the important continuous probability distribution is a normal distribution. A normal distribution. And remember that the graph is called a normal curve. It has a bell-shaped graph. Its graph is called a normal curve. It was a bell-shaped graph. So remember that to graph a continuous probability distribution, which in this case is a normal distribution, to graph this normal distribution, we use probability density function. Density function. Okay, so remember the formula, y was equal to 1 over sigma square root of 2 pi e raised to negative x minus mu squared divided by 2 sigma squared. But eventually we use a calculator to actually calculate the area below the graph. After that, we introduced z, x minus mean divided by standard deviation. It actually helps us to transform a normal distribution into a standard normal distribution. It helps to transform the normal distribution into a standard normal distribution. Remember that the graph below the standard normal distribution is equal to 1, the mean is equal to 0, and standard deviation is equal to 1. Well, after that, we talked about sampling distribution of sample statistic. Sampling distribution of sample statistic. So sample statistic, we work with mean, x bar, and what did we do? We actually define sampling distribution to be the probability distribution of a sample statistic. So sampling distribution is the probability distribution of, so it's a probability distribution of sample statistic. In this case, x bar. This sampling distribution is formed when samples of size n, repeatedly taken from the population. are taken from the population. Then we calculate the mean of those samples and we actually form a new sampling distribution. So since our focus was on X bar, the mean of the sample, if the sample statistic is X bar, then this sampling distribution is called the sampling distribution of sample means. Then this sampling distribution is called the sampling distribution of sample means. Sample means. So then we introduce one of the most important theorems in statistics, central limit theorem. Central limit theorem says if n is greater than equals to 30, then the sampling distribution of the means of the sample means is approximately normal and it has the following properties. First of all, the mean of sampling distributions of the means of the sample means is equal to the mean of the population. So the mean of the sampling distribution of sample means is equal to the mean of the population. Population mean. However, its standard deviation is going to be smaller. So standard deviation of sampling distribution of sample means is equal to the standard deviation of the population divided by square root of n. So standard deviation of the sampling distribution of sample means is equal to the standard deviation of population divided by square root of n. This is also called the standard error of thinking. Error of thinking. Okay, now what? How do we use this in? Now we're going to talk about confidence interval. So what is our goal? Our goal actually is to try to estimate the population parameter using sample statistics. This is our goal. To estimate the population parameter. What is that parameter? It can be mean, or it can be proportion, or it can be standard deviation using sample statistics. Okay, how are we going to do that? We're going to use confidence interval to actually answer this question and estimate the population parameter. Think about it this way. Suppose there is a chess club, and we want to know what is the average IQ score of people who are a member of that chess club. What is the mean IQ score of members of this club? How do we do that? So suppose you have limited time and you go there and collect a sample. And calculate the sample mean, X bar. So we try to find the mean IQ score. So we find X bar or mean of the sample. After finding the mean of the sample, since you have only one sample, you probably don't get the exact value of the mean IQ score of all members in that club. It means that in this case, we have some level of certainty, or we have some level of confidence as a measure of degree of reliability to say that, hey, you're, for example, 90% confident that, you're 95% confident that, you're 99% confident that the mean IQ score of members of this club is actually close to that sample mean. So we are 90%, 95%, or 99% confident. So in this case, we are actually talking about the level of confidence. The level of confidence. Which is denoted by C. Okay. But what is the difference? What is the difference between our actual population parameter and the rest of the sample statistics that we calculated here? Do we see any, for example, let's say a distance, the greatest distance or largest distance between the point estimate, and the population value here? So do we see any error? Of course. An error for the largest distance between X bar and population. We call this number margin of error. Margin of error. To find margin of error, we actually need our level of confidence. And finally, after finding a range of numbers, we can form and construct our confidence interval. Confidence interval. And then we can say that, hey, for example, we are 90% confident that the mean IQ score of members of this club are in between two numbers. So A, comma B. So when we are working with an interval, you have a lower bound, you have an upper bound. So you can say that we are, or I am percent, 90%, 95%, 99%, or other confidence levels. I am this much percent confident that the mean IQ score of members of this club is between A and very well. Today we're going to talk about how to build confidence interval for mean. Then we're going to move on to population proportion. Then we're going to move on to population standard deviation. 3 different processes. Okay, so let's write down our objectives here. This is for chapter 6. First, find point estimate. 2, construct a confidence interval. Confidence interval. Very well. I'm going to write down the definitions and I'm going to list all the steps here for you. Then we're going to go over examples. So first of all, when you're working with a population and you're taking samples from it, you need to make sure the sample size is greater than equals to 30 or your population is normally distributed. So we want to construct a confidence interval for mean of population for mean. 1, make sure sigma is given. 2, check if sample size is greater than equals to 30 or population is normally distributed. N is the sample size. Sample size. 3, you need to find your point estimate. The unbiased point estimate for the population mean is actually sample mean. Find the point estimate. What is that point estimate? X bar. 4, identify the level of confidence. The level of confidence denoted by C. What is a level of confidence? As I mentioned before, level of confidence is the a measure of degree of reliability. A measure of degree of reliability. Or you can say that it's the probability that the interval that you're constructing actually contains the population parameter, which in this case is your mean, or the probability that the confidence interval that you're constructing contains the population parameter, which in this case is your mean. As I mentioned before, in traditional statistic, we're using 90% confidence level, 95% confidence level, or 99% confidence level. Of course, we have other confidence level as well. In a minute, I'll show you how to connect the level of confidence and critical values. Fine. Find critical values. We have two of them, plus, minus, z sub c. So what are critical values? Critical values are actually values or numbers that separate the probable sample, the statistics, from unusual or improbable ones. Critical values are numbers, values that separates the probable sample statistic from improbable or unusual ones. So since these are z values, the z values on horizontal axis, suppose this is your normal graph, and negative ZC, positive ZC, and here you get the area in between minus ZC and positive ZC. As I mentioned, these are just critical values. Later on, we say that, hey, these two separate rejection regions from non-rejection regions. Okay, how do we find critical values? To find critical values, we can use the level of confidence, do a little bit of algebra, 1 minus the level of confidence divided by 2. You get the area on the left-hand side, you get the area on the left-hand side of this region. This is 1 minus c divided by 2. Since you have this little area on the left-hand side, you can use your inverse norm to find your ZC. So, to find critical values, we can use the level of confidence. We need 1 minus c divided by 2 and use the inverse norm. Let me use my calculator and actually calculate the critical values for these 3 levels of confidence. So our C is 90%. This is our first level of confidence that we're going to try to find the critical values for it. So here we have a normal distribution. And suppose 90% is around here, 90%. 1 minus 90%, 1 minus 0.90 is going to give you 10%. 10% divided by 2 is the area to the left, area to the right. So you get 10% divided by 2, 10% divided by 2. This 10% divided by 2 gives you just 5%. 5%. There you go. So this area, this little area to the left is 5%. Remember that to use your Z table or to use your calculator, you can just use the area that you have and find that area in the table, or use your calculator. So 5%. There is 5%. Let us find 5% here. I'm looking for 5%. So this is 50%. I don't need 50%. I'm looking for just 5%. So I don't have the exact 5%, but a number between these two is going to be my value. So negative 1.60, 60, 45 in between these two. So by using your Z table, you get ZC negative 1.645. So on the right hand side, because of symmetry, this is 0 in the middle. Because of symmetry, this is the exact same number but positive. Okay, second bars, we go to inverse norm, and the area is equal to 0.05. Negative 1.640, if you round it, you get 45. So this is plus minus 1.645. Critical values for 90% confidence level. For 95% is actually equal to plus minus 1.96. You can use your calculator or you can use the table. And for 99% confidence level, it's going to be plus minus 2.575. You either memorize these or you can always get back to your calculator, to your Z table, to find the different critical values for the confidence level given to you. After finding the critical values, in the next step, step 6, we need to find the margin of error. Margin of error. Margin of error is defined as ZC, the positive critical value, times sigma divided by square root of n. So this is called the margin of error. Or is, as we mentioned, is going to be the largest distance between the point estimate and your population parameter that you're trying to estimate. So the largest distance between point estimate, X bar, and population parameter that you're trying to estimate. Okay, after that, after finding the margin of error, we can nicely form our confidence interval. 7, so the confidence interval is equal to X bar minus margin of error, X bar plus margin of error, or you can write it this way. You can say that mean, since in this case you are trying to estimate the population parameter, which is mean. Mean is in between X bar minus margin of error and X bar plus margin of error. Let us go over one example. So in this example, we have a collection of data. An economics researcher is collecting data about grocery store employees in a county. The data listed below represents a random sample of the number of hours worked by 40 employees from several grocery stores in the county. Find a point estimate of the population mean. Okay, we're just finding a point estimate. We're not finding the confidence interval, just the point estimate. Remember that the unbiased point estimate for the population mean is sample mean. The sample mean in this case is 29.6. On page 3, we're going to use the information from page 1 and construct a confidence interval. Use the data in example page 1 to construct a 95% confidence interval for the mean number of hours worked by grocery store employees. Assume that the population standard deviation is 7.9. So 95%, it means that your C is 0.95. And here you have sigma standard deviation equals to 7.9. Let us go back to the board and write down everything. Remember that your X bar is 29.6. Page 3. In this example, our goal is to construct a confidence interval. To construct a confidence interval, CI, for population mean. We are trying to estimate population parameter value, which is in this case population mean or mean. Okay, what information are given to us? We know that X bar, we already calculated X bar, the point estimate, which is equal to 29.6. Very well. We also know that the C confidence level is equal to 95%. What else is given? Sigma or population standard deviation is also given, which is equal to 7.9. 7.9. So let us write down the steps that we have to take. First is sigma given to is M, sample size greater than 30, or you have a normally distributed population. Distributed. 3. What is X bar? Point estimate. 4, what is the confidence level? 5, what are the critical values? Plus, minus ZC. C, what is the margin of error? ZC sigma divided by square root of n, margin of error. Seven, what is your confidence interval? And how to interpret that? X bar minus margin of error, X bar plus margin of error, and interpretation. Very well. So, is sigma given to us? Yes, sigma is given. We see it here. It is 7.9. Is sample size greater than or equals to 30? If we look back to the example, you see we have n equals to 40. So n is equal to 40. 40 is greater than or equals to 30. So the second condition is also met. What is X bar? The point estimate. We calculate the point estimate to be 29.6. Check. Level of confidence. Level of confidence is equal to 95%. Check. What are the critical values? We can use our calculator, or we can just remember those important critical values. For 95%, it's going to be plus minus 1.96. So plus minus 1.96. Now let us construct the margin of error. E is equal to margin of error is equal to ZC. Remember that we're using the positive one, sigma divided by square root of n. So margin of error, ZC, which is equal to 1.96 times, what is sigma? Sigma is equal to 7.9 divided by square root of 40. Let us do the calculation. It's going to be 2.4. 2.4. So we found margin of error 2.4.